To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today also I am going to discuss with you all some extra questions related to electronics. So in the previous chapter we discussed some MCQ type questions. But here these are questions where you have to either write the answer, a short one or a long one, or maybe like this where you have to put tick and wrong for the correct and false statements. So this is extra question 2. If the statement given below is correct, mark right, and if it is incorrect, mark wrong within brackets. So this is for you all to recall what we have learned in the lesson. The positive terminal of the battery should be connected to the P terminal when biasing a PN junction diode. That is correct. You all can remember that, students, when we bias the PN junction diode. Now you have the positive and negative terminals of the battery. Now if I draw both the instances, so this is P and PN. We can connect them in two ways. Now if we connect it like that and this. So here positive, negative. Now this of course will decrease the depletion layer. So this is going to be forward biased. Why? Because the positive terminal is connected to the P junction and negative terminal is connected to the N junction, so that the electrons will be repelled from the negative terminal of the battery. That will further push the electrons in the N junction, N region, towards the depletion region. At the same time, holes also will move towards the depletion region. Therefore, the depletion region becomes thinner and thinner. Finally, when you supply a voltage that can overcome the biasing voltage, then the diode will become forward biased, or the PN junction will be forward biased. But here, when you have the positive and negative terminals connected this way, now the electrons will get attracted to the positive terminal of the battery. At the same time, electrons from the battery, the negative terminal, flows towards the positive region of the PN junction, further widening the depletion layer. So this is reverse biased. So here there will be no current flow across the PN junction. So if you want to forward bias it, positive terminal of the battery has to be connected to the P region of the PN junction diode. So if we look at the statement there, the positive terminal of the battery should be connected to the P terminal when biasing a PN junction. For the PN junction to work, we need to forward bias it. So in forward biasing, you all know that the positive terminal has to be connected to the P region of the PN junction diode. So this is correct. Then the second one. A transistor can be used as a switch and a signal amplifier. That is also correct, no? We have discussed many functions of transistors. It can be used as a signal amplifier, current amplifier, a switch, and also light dependent switch with a light sensor. So like that, we can use transistors in many ways. It can be used as a switch and a signal amplifier. Correct. Then the third one. Current flows from collector to emitter through the base in a PNP transistor. So, if we draw the symbol of a PNP transistor, you can remember these, students. We have the PNP transistor. So, this is the symbol. I draw it here. if it is a transistor. So here you all know this is the base. If we put the arrowhead here, it will be the emitter and collector. So if it is a PNP transistor, how does current flow? From the emitter to the base, then to the collector. So the arrowhead will be this way. You can remember I showed you all the regions also. In a PNP transistor, it is going to be like that. So PNP. The emitter is going to emit the holes. So the holes are going to move this way and the current also will flow in the same direction. So there you all can see current flows from collector to emitter through the base. That is wrong. Why? In a PNP transistor, current flows from emitter base to collector. So here if we look at the statement, current flows from collector to emitter through the base in a PNP transistor, it's wrong. Current flows from emitter to collector. So the third statement is incorrect. Then the fourth one, the major charge carriers of a N-type semiconductor is electrons. That's correct. Now if it is P-type holes, positive type, N-type, negative type. So negative type electrons are negative. So that is correct. Then the fifth one, the depletion layer widens and prevents the flow of current across it when a PN junction is reverse biased. I already showed you all that. Here you can see this is forward biased, reverse biased. The depletion layer widens and prevents the current from flowing. So that is also correct. The depletion layer widens and prevents the flow of current across it when a PN junction is reversed biased. So I am sure you all also marked all these statements correctly. So these are the answers for the first 5 statements. I will move on to the next slide where I continue with the same question. The sixth one. Here you can see the short terminal of an LED is the cathode. That is correct. No students, you all can remember the symbol. You can remember the diode LED. It is like a structure like this. You have the small terminal and the long terminal. So this is the long anode and that is the short cathode. Short one is the cathode. And here cathode is the negative terminal, anode is the positive terminal. So if it is an LED like that, long terminal is anode and the short terminal is cathode. So here to answer the question, you can see the short terminal of an LED is the cathode. That is correct. Then the seventh one. A solar panel is obtained by arranging a number of solar cells in series and parallel manner. That is also correct. So you all know a solar cell is a PN junction where when the light falls, the solar energy falls on the PN junction, there is an electromotive force generated and due to that electricity is generated. So we use the light energy to generate electric energy. So when many solar cells are connected in series and parallel, we get the solar panel. So that is also correct. Then the eighth one. A PN junction diode is used to prevent the damage caused to a direct current appliance by supplying power with inverted terminals because it allows current to flow only in one direction. That is correct, no students? Now PN junction diode always allows current to flow only in one direction. That is why it is able to prevent the damage caused to electric appliances if the terminals are inverted. So this statement is also correct. Then the ninth one. The very low power consumption and the long lifetimes are the reasons for the wide usage of light emitting diodes. Yes. Earlier, you all can remember light emitting diodes were used as indicators. But currently, the white light emitting diodes are usually used in lighting households. LED torches, LED bulbs, even LED headlights are available Why? Because of their long lifetime and the low power consumption. So that statement is also correct. Then the 10th one. Magnitude of voltage or current varies between 0 and a maximum value for the rectified current. That is also correct. You all are familiar with that, students. Now we have seen both half wave rectified and full wave rectified. In both these, in half wave rectified, there will be a gap, but still there is fluctuation between 0 and a particular value. If you take the full wave rectified, there also you will have a fluctuation between 0 and a particular value. So, always magnitude of voltage or current. Now, here we will have voltage or current. Here also it's going to be voltage or current. So, magnitude of voltage or current varies between 0 and a maximum value for the rectified current. So, this is the rectified current. It fluctuates between the 0 value and a maximum value there. So, here this is the maximum. Here also there is a maximum value. So, that statement is also correct. So, I am sure students you all also mark these statements correctly. So, with that I will move on to the next question. Extra question 3. Draw the circuit symbol used to represent the PN junction diode. So, you are familiar with the circuit symbol. We have for the PN junction diode, we use a triangle like that. So, that is the circuit symbol. And here you all know the direction of the current flow is going to be that way. Positive terminal of the battery has to be connected to this terminal and that will be connected to the negative terminal. So, this is the anode and that is the cathode. So, you all know current flows through this direction. So, that is the circuit symbol for a PN junction diode. Is that clear, students? So, then I will move on to the next question. Extra question 4. What happens when a battery is connected to the PN junction with its negative terminal connected to the P-type semiconductor and its positive terminal connected to the N-type semiconductor? A voltage sufficient to overcome the potential barrier is applied by the battery. So, you all know what the potential barrier is. If it is a silicon semiconductor, potential barrier is 0.7. If it is germanium, 0.3. So, here they say a battery that can supply sufficient voltage to overcome the potential barrier is supplied. So, if it is 0.7, 1.45 volt battery is more than enough. But we will see how the junctions are connected. Now, here you can see if we have a PN junction like that with the depletion layer and the batteries are connected. Here you can see, now this is P, that is N. Now, PN junction where the negative terminal connected to the P type. So, here the negative terminal connected to the P region and the positive terminal is connected to the N region. What will happen there? The electrons will get attracted this way. The electrons will start flowing this way. Electrons. And here the holes will be neutralized by electrons. So, because of that, the region will widen further. It will become more broader. And then there will be no current flowing across the PN junction. So, that means this is the reverse bias condition. So, this is the diagram where we have shown reverse bias of PN junction. So, we have to explain this. We have asked what happens when a battery is connected to the PN junction with its negative terminal connected to the P-type semiconductor and its positive terminal connected to the N-type semiconductor. So here we have to explain this. We can say when the terminals of the battery are connected to the PN junction as shown above, electrons from the N region flow towards the positive terminal of the battery and electrons from the negative terminal of the battery flow towards the P region. Because of this, the depletion layer widens further and does not allow current to flow across the PN junction. This is known as reverse biasing of a PN junction. So that is what happens. If we quickly go back and check the explanation, so you all know what happens here. This is how this happens, the depletion layer. This is the depletion region. Depletion region. What I have marked like that. That is the depletion region further widens. So there you can see. When the terminals of the battery are connected to the PN junction as shown above, electrons from the N region flow towards the positive terminal of the battery and electrons from the negative terminal of the battery, so there should be a Y, negative terminal of the battery flow towards the P region. Because of this, the depletion layer widens further and does not allow current to flow across the PN junction. This is known as reverse biasing of a PN junction. I'm sure you all can understand that, students. So you also would have given a similar explanation here. It is always better to draw the diagram and then explain. It gives a more better explanation. So with that, I will move on to the next question. Second part of the question there. Explain briefly what happens when a battery is connected to the junction with its negative terminal connected to the N-type semiconductor and its positive terminal connected to the P-type semiconductor. A voltage sufficient to overcome the potential barrier is applied by the battery. This is the opposite of what we discussed before. So here, what do? We have the PN junction there with the depletion layer, and then we connect the batteries like that. So P, N, this is the positive and negative terminal. Positive terminal connected to P and negative terminal connected to N. This is the depletion layer. What will happen here? Now the negative electrons, they are connected to the negative terminal here. So electrons will flow this way and it will push the electrons to move towards the depletion layer. At the same time, since the positive terminal is connected to the P region, there also the holes will try to move towards the depletion layer. So because of that, the depletion layer will become smaller and smaller, and when we supply the voltage that is sufficient to overcome the biasing voltage, current will start to flow across the PN junction. So that is forward biasing of a PN junction. So here of course from both sides the depletion layer will become smaller and smaller. So if we briefly explain that, when the terminals of the battery is connected as shown above to the PN junction, electrons from the negative terminal of the battery flow towards the N region and push towards the depletion layer. At the same time, holes from the P region move towards the depletion layer. Because of this, the depletion layer becomes thinner. When sufficient voltage is supplied to overcome the bias potential, current current flows across the PN junction. This is known as forward biasing. Is that okay, students? So here I have shown the diagram. This is how we connect the terminals of the battery. Positive to the P region, negative to the N region. So because of that, when the terminals of the battery is connected as shown above to the PN junction, electrons flow from the negative terminal of the battery, flow towards the N region and push towards the depletion layer. Push towards the depletion layer. And at the same time, holes from the P region move towards the depletion layer. Because of this, the depletion layer becomes thinner. And here you can see when sufficient voltage is supplied to overcome the bias potential, current flows across the PN junction. When sufficient voltage is supplied to overcome the biased potential, current flows across the PN junction. This is known as forward biasing. Is that clear, students? So I'm sure you all also wrote a similar explanation there. So when the PN junction is forward biased, current flows across it. If it is reverse biased, current does not flow across it. So for the diode to function, we need to forward bias it. It is a diode, that is a PN junction diode. So when we forward bias it, current will flow across it. That is why a diode allows the current to flow only in one direction through it. So you all can remember that. So with that, students, I will move on to the next question. Extra question 5. Illustrate using a diagram the structure of silicon at 0 Kelvin. So at 0 Kelvin, you all can remember, students, we have a lattice structure. There will be 4 silicon atoms around 1 silicon atom, and there will be bonds. They are all bonded together like that. If you are to draw the complete structure, all the electrons will be part of the bond. Silicon lattice at 0 Kelvin. Now here also this silicon will be bonded to another 4 silicon atoms. So there will be electrons. All the silicon atoms are bonded together and the electrons are present in bonds. That is the structure of silicon at 0 Kelvin. Is that clear to you all, students? So even all these silicon atoms will be bonded with other 4 silicon atoms. That is why it is a crystal lattice. You all can remember that. So this is what you need to show. With that, students, I am going to move on to the next slide. So here we have extra question 6. Write the charge carriers present in a pure intrinsic semiconductors. In a pure intrinsic semiconductors, there are both electrons and holes. Why? How does that happen? You can remember, students, we drew the silicon lattice there when it is higher temperature. More than 0 Kelvin, what happens? Now most of the electrons remain between the silicon atoms, but a few bonds are broken, and because of that, there will be a hole generated with a free electron. So a free electron and a hole. So both hole and free electrons can move. Holes act as positive charge carriers, electrons act as negative charge carriers. So because of that, both of them contribute for the conduction of current? Positively charged holes and negatively charged free electrons. So here the question is to write the charge carriers present in a pure intrinsic semiconductors. So here it is both electrons and holes. The second one, are the intrinsic semiconductors electrically neutral? Explain briefly. Are they electrically neutral? Yes. Why? Because here you can see I have already drawn the diagram. In this there are equal number of free electrons and holes. Why? Because only when the bond is broken, electron moves out of its place where it occupied previously becomes the hole. So equal number of holes and electrons. Therefore, they are electrically neutral. So here we can say, are the intrinsic semiconductors electrically neutral? Yes, because they contain equal number of free electrons, those are negative, and holes, those are positive. So they are electrically neutral, yes, because they contain equal number of free electrons which are negative charges and holes which are positive charges. So that is the answer. Then intrinsic semiconductors conduct only a small amount of current. Why is that? Because at high temperatures, only a small number of a few free electrons and holes are there. So they can conduct only a small amount of current. How can you make them to conduct electricity well? So to make them to conduct electricity well, what happens? We dope them with group 3 and group 5 elements. And when you dope them with group 3, you get the p-type semiconductor. And when you dope them with group 5 elements, you get the n-type semiconductor. So here, the question is, how can you make them to conduct electricity well? By doping them with group 3 and group 5 elements to get p-type and n-type semiconductors respectively. They can conduct electricity well. And what do we call them? Are known as extrinsic semiconductors. So when you dope them with a material, either group 3 or group 5, you get with group 3 you get p-type semiconductor, with group 5 you get n-type semiconductor. These are known as extrinsic semiconductors and they can conduct electricity well. So this is how we make them to conduct electricity well, by converting the intrinsic semiconductor to extrinsic semiconductor. I am sure you all have answered that correctly. With that, students, we'll move on to the next question. Extra question 7. The first one, explain briefly how doping with phosphorus, that is P, arsenic As or antimony Sb increases the conductivity of the semiconductors. So you need to explain briefly. So if we take phosphorus, that is P, belongs to group 5. So it has 5 valence electrons. So when silicon is doped with phosphorus, what happens there? You have the silicon lattice. One of the silicon atoms or few of the silicon atoms will be replaced by phosphorus. So let's say this particular silicon in the middle is replaced by phosphorus. Then what happens there? There are 4 bonds formed with phosphorus and silicon, because there are 4 silicon atoms surrounding phosphorus. But the phosphorus atom has 5 valence electrons. 4 had been used for the bonds, 4 covalent bonds. There will be 1 free electron. So there will be a free electron there. Now electrons are negative charges. So that means there will be more negative charges than positive charges there. Now it is not electrically neutral and it becomes an N-type, negative type semiconductor. So that is what happens here. Explain briefly how doping with phosphorus, arsenic or antimony increases the conductivity of the semiconductors. There are additional free electrons. Because of that, the conductivity increases. So we have to explain that as well. When doped with group 5 elements, there will be free electrons. Then there are more electrons than holes. The semiconductor becomes negative type, that is N-type. Electrons are the majority charge carriers. And holes are the minority charge carriers. So here the question is to explain briefly how doping with phosphorus, arsenic or antimony increases the conductivity of the semiconductors. So here we can say the free electrons contribute to increase the conductivity of the semiconductor. conduct. Or you can say because of this, the conductivity of the semiconductor increases. So here I have briefly explained it. I have shown the diagram where you get the free electrons. So here the explanation, when doped with group 5 elements, there will be free electrons. Then there are more electrons than holes. The semiconductor becomes negative type. So here the semiconductor becomes negative type, that is N-type. Electrons are the majority charge carriers and holes are the minority charge carriers. The free electrons contribute to increase the conductivity of the semiconductor. So that is how the conductivity increases. Is that clear, students? So I am sure you all also wrote a similar answer. You gave the correct explanation. So with that, we'll move on to the next question. Second part of the question. What is the name of the semiconductor produced by doping silicon with arsenic? What is the reason for that name? So already with the explanation, I have given that explanation as well. It is called the N-type semiconductor. What is the reason for the name? Because the negatively charged electrons are the majority charge carriers. So here we have said because there are more electrons and they are the majority charge carriers, because the semiconductor becomes a negative type semiconductor. More negative charges. So that is N-type semiconductor. Is that okay, students? So then with that I will move on to the next question. Extra question 8. What is biasing? First part of that, what is biasing? What do we say for that? Now we all know there is a PN junction, there is a depletion layer in the PN junction. So when we connect a battery, what do? We apply a potential difference across the PN junction using an external source. So that is what we call as biasing. So when we say what is biasing, applying a potential difference across a PN junction using an external electric source is known as biasing. So applying a potential difference across a PN junction using an external electric source is known as biasing. Then the next part, briefly explain the terms forward biasing and reverse biasing using diagrams. So if we say forward biasing, what happens there? We have the PN junction with the depletion layer connected to the battery. Then we have the same PN junction So here PN. So this is P and N, and this part is the depletion layer. So when you connect it this way, what happens? The depletion layer, because the negative electrons flow towards the negative region, that pushes towards the depletion region. At the same time, since positive potential is applied to the P region, the holes are pushed towards the depletion region. So because of that, the depletion region decreases. And finally, there will be no depletion region. And if you supply a potential enough to overcome the potential barrier, which is known as the bias potential. If it is a silicon PN junction, it is 0.7 volts. So if you supply a voltage greater than 0.7 volts, then the current will flow through the PN junction. So there, what happens? The depletion region narrows and the potential barrier is overcome. So there is current flow. So briefly explain the terms forward biasing and reverse biasing using diagrams. So here we have explained forward biasing first. Then we need to explain reverse biasing also. Reverse biasing, I will use a different color, then it's easier. Reverse biasing. So here also we can draw two PN junctions. So here what happens? Depletion layer. Here wider depletion layer. So because of that, current does not flow across the PN junction. So from here to here, what happens? Now when we connect the negative terminal to the P region and the positive terminal to the N region, electrons flow from the negative terminal to the positive terminal, more holes are neutralized. And on this side, electrons from the N region flow towards the positive terminal. Because of that also, there will be a neutral region generated there. Because of that, the depletion region widens. And therefore, current does not flow across the PN junction. So this is what you need to explain. The depletion region widens. Is that clear, students? So forward biasing and reverse biasing of the PN junction. They wanted you to explain it using diagram. If you like, you can also show the holes in the P region, electrons in the N region. That also is possible. But here I wanted to show the depletion region mainly. Here you can see this is the depletion region, a smaller region. Here it is more wider. That is the important part that you need to show. Is that clear, student? Extra question 9. The first one, what is rectification? Now you all know, you are familiar with alternate current and direct current. Alternate current, the direction of the current varies with time. So you have the positive current and negative current. If the frequency of alternating current is 50 Hz, in 1 second the direction of the current will change 50 times. So that is the alternating current. In a direct current, the direction of the current does not change with time. So if we convert the alternating current to a direct current using rectifier diodes, then that process is known as rectification. So that is what you need to write here. Okay. Converting alternate current, alternating current to direct current using rectifier diodes is known as rectification. Or we can say process of converting alternate current to direct current using rectifier diodes is known as rectification. So that is the answer for the first question. Then the second part, graphically represent direct current and alternate current. So direct current and alternate current. So here we can have potential difference or current with time, and here also voltage or current with time. If it is direct current, the curve is going to be like that. Direct current, DC. If it is alternating current, what will happen? It will change like that. Alternating current. So when you all draw the graph, students, you have to draw these curves as similarly as possible. So because it will fluctuate between the positive and negative currents, and usually it will vary between a maximum current and the zero potential. So that is the alternating current. Direct current and alternating current. So graphically represent direct current and alternating currents. I am sure you all also have done that. With that, students, I'll move on to the next slide. So here, what is smoothing? What is smoothing? Now normally when you get the rectified current, whether it's half wave rectified or full wave rectified, there is a variation in voltage between 0 and a maximum value. Now to reduce that variation, what do? We use a capacitor. So that process is known as smoothing. Reducing the variation of voltage of a rectified current by using a capacitor is known as smoothing. That is what we need to write here. Reducing the variation of voltage of a rectified current using a capacitor is known as smoothing. It can be the variation of voltage or variation of current. You all know that. So here I have said voltage, reducing the variation of voltage of a rectified current using a capacitor is known as smoothing. Then, if we look at the next question, graphically represent the direct current obtained after smoothing of half-wave rectification. So normally you have the direct current that is obtained after half-wave rectification, and that also after smoothing. So if you are to do that, so this is voltage or current and that is time. Then we have the half-wave rectified current like that. You know the reason why I have drawn it in broken lines, because what will happen is it will get rectified, and when it is trying to drop, then the capacitor will function and it will discharge. Therefore, the voltage or the current will not come down to 0. Instead, it will fluctuate like that. Is that clear, students? So, this is what happens there. So, this is the graph graphically represent the direct current obtained after smoothing of half-wave rectification. So, this is going to be the curve. Is that clear? So, then I will move on to the next question. Extra question 10. So, there they have given the circuit. You're familiar with this circuit, students. Now, if you look at it, you can see 230 volt alternating current 50 Hertz. That is what we obtain for the household from the national grid. Then here you can see this particular component. You can see the turns here and the turns here with the two lines that indicates the transformer. And the number of coils here is more, number of coils there is less. So, you know it is a step down transformer. Then here you can see that is labeled as A. And here D, you all know, is the symbol for a diode. Then C, you can see, is the symbol for a capacitor. And then you have points L and M. And here you have this symbol that is R, that is a resistor. So, I am sure you all can recall what we have discussed. This is the process where we do a half-wave rectification including smoothing. So, the output will be smoothing of half-wave rectified current. So, that is why we use the capacitor for smoothing. One diode to give a half-wave rectification. You can remember that. So, the first question, write the name of the circuit given above. Smoothing of half-wave rectified. So, smoothing of half-wave rectified. You can say rectified or rectified current. Then the second part of the question, write the name of the components represented by the symbols indicated by the letters given below. A, what is A? It is a step-down transformer. Step-down transformer. Then C, what is C? C is a capacitor. You can see there, capacitor. And then D, what is D? D is a diode or rectifier diode. I will write it as rectifier diode. Diode. You can even just write it as diode, leaving this rectifier part out because we use the normal PN junction diode. You can even mention it as PN junction diode. That is also fine. PN junction diode. They all correspond to the same diode. Rectifier diode, diode or PN junction diode. One of the answers is fine. Then, Here you can see the third question. Write two methods used to obtain an alternating current, AC current. How can you get that? We can use a bicycle dynamo to get the alternating current, or you can use an alternating current generator. Two ways. So, bicycle dynamo or alternating current generator. One of those can be used, or those are the two methods by which you can obtain an AC current. So then the last part of the question, what is the function of the circuit given above? What is the function? Alternating current is converted to direct current, but there is only a half wave rectification taking place, and after that the current is smooth. So there conversion of or rectification of current as well as smoothing takes place. What is the function of the circuit given above? The alternating current undergoes half wave rectification and smoothing. So that is the function of the above circuit. Now here, since I have already written the name there, smoothing of half wave rectified, because of that I didn't write the same name for the last question. I have written the function in a little bit more elaborate manner. So the alternating current undergoes half wave rectification and smoothing. Is that clear, student? So with that, I am going to end this chapter, and in the next chapter also I will discuss some more extra questions with you.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.